the main objective of this paper is to provide a step-by-step guidance how these EHR works using GANs. So in this paper, the authors address the guidance of how these process for structured synthetic EHR data generation, and this they try to evaluate the quality of synthetic data terms like utility, privacy, and fairness to uh, to make it effectiveness for various healthcare applications. So the key findings of this research is uh, these GAN models are effectively generate structured EHR data, and it enhances machine learning models, and it 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 reduces the privacy risks in synthetic data. And the challenge that here representing rare disease and it maintaining record level constraints, and here the trade-offs is utility, privacy, and fairness. So these three it exists in this paper. So the abstract of this paper is many people use this patient data to improve healthcare, and uh, but to get real data is hard due to some privacy. So we use mimic data set uh, from real we produce fake synthetic data. So these researchers develop better AI models without violating patient privacy, and it can help uh, balance data sets and improve AI fairness. Methodology here, we have what are the methodologies, what are the methods that used by the researchers, and we have data collection and pre-processing, and we used mimic data set, and it's publicly available EHR data set, and it have some structured data diagnosis and some key health indicators, and it converted ICD 9 and 10, it combined both, and it have taken the data, and here it simplified into categories it simplified categories into code, because uh, it will make better to use. So GAN training for data generation here used EMRW GAN, and it is a specific GAN variant to generate synthetic EHR data. So this data is used to train GAN. So this post processing of synthetic data, and here we apply normalization and rounding to get the realistic values for different variable types. So data quality evaluation, here we have three data quality, and its utility, privacy, and fairness, and these three used for synthetic data that used for multiple evaluation metrics. And this is the process how these uh, data how these process is going on. And first we have data pre-processing, model training, and data generation and post processing, and data quality evaluation. In data processing we have to remove outliers, and we have to handle missing values, how whether they have any missing values in the data, and we have normalize continuous variables and handle concepts with low prevalence. And we have model training, non-conditional training and conditional training, and we have data generation which use for non-conditional and conditional, and from that is determine composition. So data quality evaluation, we have at first we have three, privacy is the most important factor here. So this is the GAN architecture, and we have input voice. We have to give the data. From that it have generator, and from generator we have two real EHR and synthetic EHRs. From that it have connect discriminator, we have generator and discriminator in GAN architecture. So from that it will provide real or fake, uh, it will see whether it's real or fake, and if not, and it will go back and again it start the process. So it's back propagation. And how this generator works in this paper. Like first, like input to generator, what we are giving to the generator. So it have like random voice plus structured EHR features like age, diagnosis, like everything. And this noise helps to create new realistic patient records. So what generator is like do after the input data? So it convert voice into EHR record, and that resembles real patient data. So discriminator task is to receive both real and synthetic records, and it tries to classify whether the data is real or synthetic. So we have adversarial training, and in this adversarial training, we have like generator learns from discriminator feedback, like what discriminator is giving to generator to improve the data quality. So if the data quality is not good, and again the generator will shift to like discriminator shift to generator, and again the generator learns from the feedback. So after doing multiple iterations, so the synthetic data becomes like indistinguishable from real EHR data. So here we have limitations and challenges, and in this paper, like we have seen like rare diseases are not well represented. Like we like GAN struggles with lower frequency diagnosis. So here it's not supposed to give the most realistic data. So sometimes it may give the unrealistic data also. So clinical inconsistencies may occur, like if we don't like it don't have like medical rules to prevent uh, biologically impossible records. And GAN requires multiple times that it needed to give the best model. So if we do 5 to 6 trainings, so it will improve up to 5 trainings, and it may give the data into realistic. So we used to train the data more. So result and interpretation here, like the study gives several key findings, and it related to synthetic EHR data generation, quality evaluation, and trades-off between these three. So here, synthetic EHR data generation and utility. So GAN successfully captured the statistical characteristics of real EHR data. So the privacy, like how in synthetic data, how the privacy is built. So it reduces privacy risks compared to real patient records, because we are taking synthetic EHR. So maybe the privacy compared to real data, it's very less. So so it reduces the risk of the data. So here, like in this paper, we have like up to 5 runs. After 5 runs, we got uh, like real data, like compared to these runs, and we have after 5 runs, we have got some better result. So this GANs really required a lot of multiple trainings. So after multiple trainings, we will get the real data. So compared to previous, like this paper and previous paper, how they uh, uh, done better than previous paper. So about synthetic data generation, this GAN model successfully captures EHR patterns. So previous study, it also generated like uh, it also generated EHR data, but compared to last previous studies, this paper gives better than a previous paper. And risks, and here the risk is reduced but not eliminated, because we have like some more risk to uh, eliminate also, because we haven't reduced overall risk. And for before study, we have like synthetic data is it's not particularly safe, like perfectly safe. And it's not like it have more problems than now. So this one is better, like it's not eliminated, but it's now it's better to reduce, like somewhat reduced. And clinical consistency, like uh Here in this paper, GAN having automatically prevent medical errors, because in this GAN in this paper, we have like uh, if we have like some data, it will give us some other result. It won't give like the real data if it's not really occur, but also these data will give some uh, like errors. So previous study, it's not about medical rules, and it's not unless it's constrained. So machine learning performances and ML models train on synthetic data and perform well as real data. But prior work, it showing synthetic data and support ML training. So handling rare disease, like GAN failed to accurately present rare conditions. Like it's not because it won't present the rare conditions. So maybe we can use some other process like to get this one. So before study also, it's have low prevalence disease are hard to predict with synthetic data. It will take like it won't get sufficient data to get these rare conditions and these utility and privacy. So here we have like more privacy, and we reduced utility also. But in other studies, this provides like ever it provides the detailed evaluation, but not completely the measures that reduces both privacy and utility. And discussion and implications here, like we like enhancing data access for research and AI development, and it reduces bias, and it improves fairness in AI models, and improving medical education and training, ensuring privacy in healthcare data sharing, and augmenting real world data. And challenges, like what are the challenges or future directions that authors provided here, like we have only three, like in this paper, like we can't get realistic patient data for rare diseases. It's the main challenge we have, like GAN used to struggle for more, and clinical inconsistencies in synthetic data, and limited understanding of how GAN scale, like how it works. Like it's hard to understand uh, the that how it's working. And critic and evaluation of the paper, and like strength and weakness, and like it given the detailed methodology, and it have like it given full detail of data evaluation, and how the data is like transparency, reproducibility, and it address real world applications challenges, and it given like multiple runs, like after multiple runs how we will get the result. If we have low runs, how we will get the result. So it mentioned clearly. But but I will not like they haven't mentioned more detail, but they have like step by step guide. And the weakness of this paper is it focus only structured data, and it have the like its weakness is like rare disease representation. It won't represent, and it does not generate time series data. So these are the weakness of the paper. And the overall conclusion of this is the study have like uh, clear methodology how these GAN works with EHR and synthetic data, and how the further improvements we gonna need for after reading this paper. Like we have rare disease modeling and some privacy, because it's not eliminated full privacy. We have like only limited privacy. We have to uh, eliminate full privacy also. We can see the models, and we can eliminate that too. And this is like we have I have read about VAE also, like VAE and CAN. And for V, like uh, here the main model used like GAN for this paper, and under like we have another paper like VGAN. So this GAN represents the structured data, and here it's like the um, uh, it's like based on graphical data. So this data type is high quality for the records, and it captures the synthetic distributions. For variational autoencoder, it have graph based structures, and it represents uh, long term correlations between medical events. So the limitations of both papers, like in GAN, we haven't captured time dependent patient history. Like it, it don't have time series, so it's hard to get rare disease also. But in VAE, it's required um, graph based EHR representation, and it if we have more patient data, more patient graphs, so it have some difficulty to get that. And for privacy considerations, GAN reduces privacy, and but VAE have strong privacy uh, prevention preservation by generating new patient trajectories, and it uses noise injection to prevent data leakage. And for future directions, for GAN, we can like improve rare diseases and clinical consistency. In VAE, in VGAN, we have like multimodal EHR, like images, like reports, like how whether they are like how they are recovering everything. We can get the report, and integrating additional metadata for patient graphs, and testing for fairness uh, across the patient groups. And real world application, so AI model training on structured patient data in GAN, and medical research using de-identified records. So in vegan, we have like patient histories for clinical modeling, and this medical decision support gives realistic patient progressions. And and in this paper, overall, like I have studied, like they given a clear guidance like how these scans used for these structured data, but due to like some unrealistic data, so it cannot produce a good result. So if we got some other GAN, like better than this GAN, if we go for some other models, maybe we can reduce that um, uh, um, the privacy. We can increase the privacy, and we can get realistic data more. So I'm I'm thinking to study some other papers to cover these problems as possible, if possible, to get.
So Hiva, I'm already in another meeting, but I post some question in the chat. So maybe you guys can discuss this. Like, I want to see the detailed mechanism of these methods. What are the non-condition? What's the condition mean? And how would you determine what is real or fake? I'm not going to read the rest, but I'm just trying to use this as a discussion point for you guys to discuss. Ryan, can you take over this?
Yep, sure. Hi, Ema. So can you see the
Yeah,
questions in the chat?
yeah, no, I see now. Like,
Okay, so I think first and foremost, I think Dr. Chen asked about the details of, I think in the slides you mentioned that they use EMR WGAN earlier in the
yeah,
slides.
yeah.
Yeah, do you have any like details on how the model works, or either
Yeah,
either how the
but
model works or the performance of the model?
yeah, I don't have like full detail of that, but uh, like in medical records, like in medical records, these WGAN like used. Um,
Hello?
Are you audible, Ryan?
Yeah, I can hear you.
Yeah, yeah. So this WGAN is like it designed to train and it improves the ability of realistic data because we have like uh, unrealistic data in this GAN. So if we use, we can reduce some of the data of this unrealistic um uh, methods to reduce the privacy. So in most of the medical background, so these WGAN is used more. And I'm not sure about the like these WGAN, but maybe I will do some reading about this more detailed.
Okay. I think in the slides, can you go back to the I think it was the data processing tables and trainings.
Yeah.
There's like conditions and non-conditions training. Can you like explain more about that?
Oh,
Yep, this slide.
okay. Mm, like
Can you go back one
mm,
slide?
one back here.
Yeah. Yeah, this one, the non-conditional training and non-conditional generations and conditional, what's the difference between those two?
In like we have like model training, and here in Gen AI, like it's like generative GAN, we have like generator and discriminator both. Here we have like conditional and non-conditional, and it works like like this model has like overall data distribution, and it have uh, like the real data as a whole, but does not control for specific attributes. So it's like non-conditional training. So it does not give uh, a specific about the data set, like how these like I said before, like these producing non-realistic data. Like if we don't have that like that disease or something, but it will provide like some missing data, like it will provide uh, some different data in that place. So due to that it won't we are, like it does not get like the data which we we have to get to that. So here we use like non using non-conditional timing. So then like we can get how it's like. If we see here like I think here it's not mentioned. So here we like it's have back propagation. So here if we do like two, like non-condition training and condition training.
Hmm. Oh, okay.
But like these models are like um, just learn how these process have taken, but I want to know more detail, like how it because in medical I'm not sure how it's going to work because like it's somewhat new. So I want to refer more about these. So that's why I was revising some other papers also, like what the actually refers.
Okay. So in this like training, for example, and non-conditional and conditional, do they share the same like pipeline like with the one you showed earlier in with the next
Uh,
slide?
okay, this one.
Yeah, so it's just different conditions with the same architecture here.
Yeah, this architecture is like about uh, like how these data is referred to real or fake. Like how we gonna uh, divide both the things. It's not mean to this one, but only for training the model. Like how we gonna uh, this is about only uh um, how I have to say, it's not connected with this model training. It's about the data. It's about the data correction. So if like in non-conditional training, like we don't have uh we it's like it's overall contribution of real data, and it tries to replicate the original data.
Okay,
So we
okay.
have in this non-conditional training also we have some data processing and how to train the model. Like if we have a generator and it receives a random voice. Okay, so here if we see we have a random voice, and for non-conditional GAN. So here it will take non like voice, and it refers to synthetic EHR, because from real data we are going to generate replication like synthetic data. So like this, if for non-conditional GAN we are going to um, back propagate if the data is not the real. Like if it's not showing the real data, then we are going to uh, generate it, and again we have to do the uh, whole process like data preprocessing and training everything, and again we have to send the data to discriminator. If it refers to fully uh, like whether it's representing the real or fake, then we have to stop that data uh, training, or else again we have to train every uh, models to uh, get the correct data. Like if
Okay.
it's not
Um,
correct, maybe I will read again, and I will get back to you later.
okay, sure, sure. So from this architecture, how do you determine which one is real or fake? So you use the discriminator, or what's that Wasserstein divergence?
Here we have generator and discriminator. So
Mm-hmm.
this generator is like uh, it
They
use
generate the
data.
synthetic.
Yeah, synthetic EHR. So
Mm-hmm.
it's we have like one like the real data we are going to take, but from the real data we are going to uh, take the synthetic EHR. So what the generator does is it learns to create synthetic data that mimics real EHR data.
Yeah, but how do you exactly determine which one is real and which one is fake? I think how do you
It's
how like you score them? Because in a sense you need a ground truth to, compare which one is fake and which one is real.
mm, yeah, uh like if we send these data like discriminator will will shows the what the real or fake, and uh like
Okay.
mm, this generator is used to create the synthetic data. It's the process of for generator, but the main work that done is discriminator.
Okay.
So
So
it will
what
mention
about
whether
what about
it's
that Yeah, sorry, what about the Wasserstein divergence there? Real or fake Wasserstein's divergence?
uh, like like we are using WGAN, right?
Oh,
So
okay.
yeah, that's the GAN for like for that it will show like whether it's uh fake or real, the data
Okay,
which.
okay, I see. Okay, so yeah, thank you. Next question, I think it's about computing power. Comparing to VAE and GAN. Do you have any idea or like what's the comparison between these two models? So what I know is GAN usually takes lots of computing power to
Yeah.
train both the generator and discriminator, but I'm not really sure about VAE. Do you have any more, comparison with computing power in terms of these two architectures?
uh I think like GAE also need like more, because like GAN used for it no, like VAE is for it's also need more computational power and data preparation, like both have more computational power, not the thing, because VAE also have like want more patient data, and it can't handle large data sets. So
Okay.
like VA, like both it uses like more computational power to get the data, because graph needs more structure like data than GAN. I think
Sorry, did you say that VAE needs more computing power than GAN?
mm, yeah, I think same, not more.
Okay.
I think
Okay, well, yeah, maybe you can do more, some reading
yeah,
about this,
these
comparison
questions,
between
yeah,
these
yeah,
models.
yes,
Hmm.
yes, yes.
So,
I
regarding to this WGAN, do you have any code? Do they provide any code from the paper that
uh
we can, go through?
um, like I have seen, but I haven't uh, like I haven't seen really more about the code, like.
Okay, that's okay. Maybe you can
Yes,
just,
maybe
share with
like I will
us
I
in
will
the.
yeah, I will just see the code and I will just do, because this process I want a lab, but I don't have it. So from one past 1 week
Okay.
I don't have my laptop, so it's hard to get study for this. So maybe I will answer
Yeah,
every question later. I will get study.
yeah, no worries. Maybe you can share the code with, Dr. Chen and me and Weir as well.
Yeah, yeah, okay. Yeah, yeah.
Maybe put it in the OneNote so we can, go
Yeah,
through
okay,
the
okay.
code together.
Okay, okay.
Mm-hmm. I think last questions from Dr. Chen is about the limitations. He mentioned about low frequency diagnosis and extensive training.
Yeah, it's like about diagnosis, like for GAN,
Mm-hmm.
like we have the data like age and sex, like male or female. So the thing they mentioned, like for example, like what they haven't exactly mentioned what these low frequency diagnosis, but they just given example like about I will show like if we have like mm, what is yeah here, and like if I say like for example, if like we have like male and female, like female if we have like there is an option like whether she's pregnant or not, like something which man
Mm-hmm. Mm-hmm.
couldn't have. So but here if we have
Yes.
like it shows for male also, it's showing like pregnant or like some
Pregnancy. Okay.
different, yeah. So that's the problem, like here it it's not well
Mm-hmm.
represented.
Yeah, again, I think with this we can do, more comparison with VAE. Do this like
Yeah, yeah,
limitations only show up in GAN or VAE, show this limitation as well? Because
okay.
we just want a more thorough comparisons to see how each model performs, I think.
Yeah, I just like seen how this works. Like I haven't gone detail about this, but yeah, I will go more detail about these two more.
Mm-hmm. And I'm quite, curious about the multiple training runs were needed to find the best model. So is that like each training they just adjust different, hyperparameters, like different batch size or different variables to find the best model? Is that what you mean by multiple training?
Yeah, 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 yeah. Like uh if like in GAN, like if we do one run, so
Mm-hmm.
it will show like some data, but not it won't give the correct way. So if we give some like corrections like in it, uh, like if we change some of the parameters, like we have a lot of parameters here, like age, everything. So if we
Okay.
change some of the parameters like that, so then we will get, after multiple runs, then we will get which one gives the correct to recognize, like to get the real output. So we
Okay.
want to change for every run.
I see. So, I think that's pretty interesting because in machine learning, there's a like a there's a way to, sort of select which parameters is the best for your
Good.
training.
Yes, yes, yes. Mm-mm.
So can we also do that to, avoid this multiple training and just find which parameters
Ah,
is the
I
best?
think in GAN we can't, because here like in GAN we have like getting the data which is real or not. It will take a lot of um, process. So uh, if like, because discriminator is not like it can't easily find more like whether it's the correct or not. So due to multiple runs, it may learn the data whether the data is correct or not. So that's
Okay.
why we are going to do multiple models for discriminator, like to get the correct data.
Okay. I see.
So I think it's not possible to change and do without runs.
Okay. I see. Well, I think that's all the questions from Dr. Chen and me.
I
So I
will,
guess just do, more comparison of what we talked about earlier, about the either computing power, also the code, and yeah,
yeah, yeah.
about these
And
limitations
about
with VAE.
yeah, limitations, and about WGAN too. So I will learn, and I
Yes,
will maybe next meeting I will
Wednesday.
present about this.
Okay. Well, thanks, Hima. I think that'll be
Thank you.
all for today. Thank you.
Thank you. Okay.